Okay, we'll go on to another question now. This one here is the last thing that I copied by the looks of things. That's okay. It's good. Whoops. Here's a two-dimensional problem. Does somebody want to describe for me, please, what it is that how do we solve this problem? What is the first thing that you do? We've got what we've got here. I'll just paint a picture for you. We've got a charge here, Q1, 2 millicoulombs. We've got a charge here, Q2, 1 millicoulomb. Milli is 10 to the minus 3. And we have some point A in the same plane as those two charges, but this is a two-dimensional problem. How do we solve this problem using the principle of superposition? Yes, using physics terms, we say the electric field E, the electric field at A due to Q1, and we'll solve that. And over here we'll solve the electric field at A due to Q2. Then what will we do? Yeah, this one's a nice problem. We're going to use Pythagoras to solve this resultant electric field, aren't we, at this point, due to the two charges. Have a go at this one, please. I think the text in this case is incorrect. So the last class, the other class, said that the text is incorrect for this problem. Shh, please. So milli, of course, is, I haven't drawn a very good 3 there, to the power of minus 3. Can somebody confirm that number for me, please? So here we go. We've got the magnitude of the electric field at A due to those two charges now. The magnitude of the electric field. We also need to show the direction, don't we? And the electric field at A due to Q1, that's what we're saying over here. E at A due to Q1 is, of course, away from A if Q1 is positive. Imagine small positive test charge. So I might say away from Q1. And here, because it's negative, toward Q2. And the diagram shows that. It's drawn the vectors there. 1 by 10 to the 6 and 1.125 by 10 to the 6. So they're similar. This vector here, they've drawn just the slightest little bit longer than this one. and we have to do a vector addition of the two. Okay, I'll draw some straight lines. So at approximately the right angle, I'm going to add them like this. Using Pythagoras, I'll call this R, the resultant. We got this answer here for the resultant there. Resultant E, thank you. What am I missing? You need to put a direction in, don't you? Now remember, we'll just have a look at this diagram up here. And all I've done is I've taken this diagram, or I've taken this E1, or E2, sorry, and moved it up to here. Okay, that's all I've done. And this is our resultant here. I'll put it in red. And I'll draw a nice straight line there for our R. And so we might say, we might put a theta in here. I'll put a little theta for my angle in light blue. Theta. We know the length of that. Opposite over adjacent, we're going to go tan theta. Theta equals, which one is that? That's the 1 by 10 to the 6, isn't it? Opposite. Yeah. I'll just skip straight ahead and say theta is equal to 41.6 degrees, so the book says. And the book says you're going to have to say this value relative to something, and the book does this below the line joining Q1 and A. And so that just says Q1 and A, so below this line here. Pictorial representation of electric fields. We draw, of course, electric fields using what we call field lines. So if we have some charge here, and I say that that charge is positive, I often say that it's a proton or something like that, an elementary particle with positive charge. Well, at this stage, it's an elementary particle. I can give it direction. How do I know to give it direction, or which direction to give it? Can you remember? Yeah, you've got to place a positive. The best way to remember it is to place a positive test charge in the area around the charged particle. And what does that positive test charge do? In this case, likes repel each other. And so the positive test charge would move out radially from the proton. I'll draw in that small positive test charge. It is a little q with a sub plus sign next to it. It would move away. If I drew an electron, I know these aren't to scale, of course. Electron is much smaller than that. 1/2000th, 1/860th or something like that. 1,860 times smaller. Now, if you have a look at the size of this guy, the mass has a mass of 1.673 by 10 to the minus 27 kilos. And this one is 909.11 by 10 to the minus 31 kilograms. Now, that's a value of, what, 10,000 or thereabouts? So the mass is quite a lot smaller. And essentially what they do is they say that the proton has mass, and yet the electron doesn't really have that much mass at all. So this is a lot less massive, yes. Anyway, so back to E fields. Electric field lines are lines of force. What is an electric field? Can anybody tell me what an electric field is? The electric field is a modification of the area around some charge, whatever that may be, that charged particle or just charge, we say. And what is that modification? Well, and I already said this prior, I hope you remembered that if this charged particle is in intergalactic space, sitting by itself, does the electric field exist? The only reason that we know that it exists is because it applies a force to any charged particle put in its field. Okay. Otherwise, nothing happens at all. If the field line is curved, so let's draw a curved field line here. Here's a field line curved. They can curve. What is the direction of the electric field at any point on that field line, do you think? Yeah, it's a tangent. The direction of the field Is this possible? Okay, that is. Doesn't look possible. Field lines may never cross. There's an electric field. Here's another electric field. Which one is stronger? Yes. The magnitude of the field is represented. Is represented by the number of field lines per unit area. When I say unit area, I might choose an area, and I think I've said this before. And if I use the same area over here, or a similar area over here, there's more field lines in here, isn't there? 4. Just to be sure. I'm not being sarcastic. Very good. Let's have a look at a diagram of some field lines. I'll let some people finish. Question. Never cross. Oh, what can I do? Yeah, okay. Can or may. Never cross. Is that too ambiguous now? Question. Please. Yes. Yeah. Yeah. Can they cross over a little bit? What's the big red X here? They're really crossing over, aren't they? Okay. Yeah. Yeah. No. Okay. Yeah. Even this, just a little bit. Can't. Field lines can or may never cross. Here's a pictorial representation. Does anybody know what this is called? Yeah. This one here is What's funny? Here we have a positive charge and a negative charge. We call this a dipole. Dipole. And you'll notice that from the positive side, the field lines go away, but they go towards the negative. And they take a more direct route the closer they are to that negative. And that has to do with the strength because of the distance. Okay, of course. Notice between the two, between the dipoles, it is a straight line. Shortest distance between the two objects. Straight line between the two. They go away from the positive and toward the negative. Here we have two positive not isolated charges. We have two positive charges near each other. They, of course, the field lines still never cross, and they go away from this positive charge, but they also go away from this positive charge. If you put a little small positive test charge in there, it would sort of go off in this direction, up or down. Okay. Let's see. What time is it? 1:15. Any questions about today? The next concept an infinite charged plate. Here's an idea. If we have next lesson then.